Okay, so good afternoon, everyone, and welcome to the session about functional commitments and proofs and MPC. And I'm Khoa Nguyen, the chair of the session. There are three papers to be presented in the session. The first one is Zero Knowledge Functional Elementary Databases by Xin-Shuang Zhang and Eden, and Xin-Shuang will give the presentation.
Thank you for the afternoon, everyone. Yeah, I'm glad to present our paper. Knowledge functional elementary databases. Hello. I'm Jian Zhang. It's a joint work with Eden. First, let me start from the network. So consider the following scenario. Let me be an elementary database with a set of key value pairs, and for each kx, there is most one affiliated value such that x belongs to D. Suppose the database owner knows such databases D, and the client might want to query. For example, he might ask that kx belongs to D, and what's the value associated with that. It's a common scenario with it's a common scenario in the real world, and there are many two security concerns. The first one is that the database owner cannot answer the queries constantly. And the second is that the client cannot learn extra knowledge. You know, in some situations, we cannot that make the database public. So there are no elementary databases designed for this scenario. It allows the database owner to commitment its database and later convincingly answer the query. Specifically, it allows the computer to generate the proof to show the answer is consistent with the commitment. And the TTP should identify the soundness security and the zero knowledge security. The soundness security requires that the computer cannot answer the queries inconsistently, and the zero knowledge requires that the commitment and the proof will not reveal any extra knowledge. And it also requires that the size of the database should not be revealed either. GDP have various applications. For example, it can be used in end-to-end encrypted communication systems for providing an auditable and variable directory of their users' public keys. In our paper, we mainly focus on the queries supported by PTDB. So most PTDB constructions follow the paradigm of GSPL, and only support the memory queries that we shown above. And the best result is the level zero knowledge passive elementary databases. It modifies GSPL's paradigm and supports rank queries over keys and or values. So as you can see, all existing constructions only support very limited queries, and we have a question that can we construct CKDB supporting richer queries, for example, the function queries, the functional queries, in the form of that the client requires the command to return all records in the databases that specifying that F on input a secured F on input the record output one. So this question is actually not trivial. I will show a new attempt that one might commit its databases first, and then use the snap scheme to prove that its answer is consistent with the commitment. However, this attempt will still use the potential revelation of the database size. That's because, as far as I know, almost all these maps expose the length of the witness. And for generalized functional query, the witness must include all records in the database. So now let me introduce our contribution. In our paper, we put forward a new notion called the zero-knowledge functional elementary databases. It allows the most generalized functional queries. That is, for any Boolean secured app, clients can query that determine all records actually belong to D, satisfying F actually equals 1. And the DKFDB should satisfy function binding property and the zero knowledge property. Here, the function binding property can be regarded as a functional query version of service. It provides the committer answering the query in context. In our paper, we present a construction based on unknown order group, and its process is only linear to the bit length of the top and the size of query secure, and it is independent of the size of database. And our construction is secure in the random oracle model and the joint group model. Our technical contribution is twofold. First, we develop a new version of their knowledge set. It supports combined operation queries on commented sets. For example, the client could query the committer to return the, for example, the intersection of some committed sets. Here, DKS is the set version of DKDB, the commit set rather than databases. And the combined operation can be regarded as secured with its intersection, union, and set difference. And we also develop a new transformation technique. It transforms the query of Boolean secured into a query of combined operations on relative sets. First, let me show how to construct the new variant of DKS. The key point is to prove the set relation on committed sets. So let me start from the famous ISA accumulators. ISA accumulators is based on unknown order groups such as ISA group or class group. And to comment a set, one jumps the hash each element in the set to frame and compute G to the product of this prime. Let me consider how to prove the set relation as the accumulator. Here we consider three basic set of relation. That's the section, union, and the set difference. These set relations can be reduced to some simple set relations like disjoint relation and the union among disjoint relation. The proof of basic set relation on committed set can be transformed into the proof of coupled relation and the DDH relation. That's because we can find that suppose J0 and J1 are disjoint, then the exponents of their commitment are coupled. And similarly, suppose U, J0, J1 belong to the union among disjoint relation, then their commitments consist of DDH tuple. So there are several works shows that the IC accumulators can be converted into DKS by adding randomness R to provide a private. And the membership and non-membership relation can be put in zero knowledge too. However, the question is that the proof of basic set relation over DKS can no longer be transformed into co-privilege and DDH relation due to the extent of randomness. Key observation here is that in DKS commitment, randomness is sampled from a small and bounded range. So let A be disjoint set. Then, although the exponents of their commitments are no longer corporate, their great common divisor is still small. And similar, suppose U is the union of the destroyed set A and B. Their commitments, although it's not a digital tuple now, but they is still close to a digital tuple. We call about two relations as pseudo coprime relation and pseudo DDH relation. To prove this pseudo relations, we need two talks. The first one is no sigma protocol, but one is the DL relation, and the second is the new variant of beneath the argument for multidimensional DL relation. We need to note that both of our protocols only achieve weak size due to that computing the institute of random elements on the group is hard. But luckily it is still sufficient for our construction. So to prove the pseudo-coprime relation, first from the Bernoulli's lemma, we can transform the origin proof into a proof that there is the integer a and b such that u to the a times v to the b equals g to the great common divisor, and the great common divisor is smaller than t. And by adding randomness for masking, we can transform the proof into two parts as shown in the slide. The first part can be used can be proved by the beneath their knowledge protocol, and the second part can be proved by the Snow's sigma protocol. However, this protocol only achieve weak size. That is, the great common divisor of the exponent might be larger than t, but it is still bounded by a proper upper bound. And this protocol can be transformed into the non-interactive version by the Samuel heuristic. Similarly, we can prove the pseudo DDH relation here due to time limits with I skipped it here. Now we can use the similar approach as IC accumulators to prove the basic set relation over the commitment from our protocols for pseudo relations. And the result of knowledge protocol only satisfy a special purpose soundness. That states that the ability of a prover generating membership or non-membership relation proof, membership and non-membership proof has to be consistent with the proved set operation. For example, suppose a committed set I has been proved to be the intersection of committed set A and B. Then proof showing that X belongs to I can be used to generate another two proof showing that X belongs to A and B. Next, proof bit by bit, we can get the proof for combined set operation queries, and the result detail scheme satisfying the standard function findings. In fact, in our paper, we show that any adversary breaking the function binding property can be will lead to a contract proof, contract membership proof and non-membership proof, and therefore breaking the strong IC assumption. Next, let me show how to transform the queries. Our goal here is to transform the query of Boolean secured F over set S into a query of combined operation Q on relative set SID. Here, SID is the set X the set of elements X in S, satisfying that its S bit is B. So let me consider Boolean secured F. You can find that when running F on an int, then every wire in F has a deterministic value. It is quite neutral. You can find an example on the slide. So when running F on each element in a set S, according to the value of Y, each yi can be associated with two sets SIB. SIB is the set that is a set of elements X in S satisfying that the value of Sy of Fx is B. Then we have several key observations. First, for input y I, SIB is exactly the reaction set we defined in our goal. That is, they are also the input of the combined operation. And sorry, there is a mistake. And the second point is that for the output y, the second set associated with the output y as output, the second set associated with the output y is exactly the answer of the Boolean security query. And third, for any AND gate in F with input y A and B and output y C, and C0 is the union of FA0 and FB0, and FC1 is the intersection of FA1 and FB1. And similarly, we can give the relation for OR gate and NOT gate. Now, as the example shown on the slide, gate by gate, we can express any associated set, including the set associated to the output y, into the output of a combined operation into the rest set. So remember that the second set associated to the output y, there is SU1. SU1 is exactly the answer of the Boolean secured query. So that concludes the transformation. Now we can conduct the knowledge functional elementary databases. So to commit a database, we first use the DKL scheme to commit all the large set, and then use DKDB scheme, a standard DKDB scheme to commit with the database D. To prove the questions of the answer of Boolean secured query, we first transform F into combined operation Q, and then use the membership and the non-membership proof to show the correctness of the red set, and then use the proof of set operation for the query to show the correctness of the answer of the output of the Boolean secured. And then use the proof of DKDB to show the validness of the associated value weight. And that's the performance of our graphic. You can find the proof size is only linear to the length of the code and the size of secure. Thank you for attention. Any questions?
Is there any question from the audience? We have time for questions.
So in your final thing for the DKDB, you committed two things, including one set and the database. Two servers committed to the database. And so how do you prove that these two commitments are consistent with each other?
You mean this one?
So this practice of SBI. So does this have to be repeated for every proof? Every time you have to prove this?
Yes, you need to prove every yes, and for each set SBR you can aggressive the proof.
Okay, so this can be reused.
No, you cannot use for.
Okay, I see. Thank you.
Any other questions? So I have a couple of questions. So in your construction of your set from the ISA accumulator, so is the cardinality of the set hidden? The size of the set is not hidden. Yes, so the question is whether the zero knowledge set hides the size of the set.
I'm sorry, what?
Means zero knowledge database, so it's hide the size of the database, right? How about zero knowledge set? So can the prover hide the size of the set when answering the queries?
Yes, the size of the business might be huge, and so the yes, and the proof for the proof showing that the set operation or the commit set is independent from the set of the set.
Question from the audience.
I have a question about is that your TKD can be update efficient or batch efficient? Did you have this function?
Yes, it can be updated because as the accumulator can be updated.
So the size of the update information is linear or sublinear. Where the data size.
I think it is independent from the size of the databases, and it is linear to the length of the report, bit length of the report.
Oh, okay. Thank you very much.
Another question. So your construction, your model, in fact, is improved limited on work in terms of functionality, right? But limited on work actually is well, based on lattice assumptions. So have you considered obtaining database construction for your functional elementary database? And what could be the difficulty?
You mean can we conduct the from other assumptions?
Yeah, what maybe in your second slide you mentioned debated on work on database, right? But I remember in that paper they constructed a lattice-based construction. So have you considered instantiate your model on the lattice assumption?
Okay, the difficulty is that if you want to have the size of your databases, you actually means a kind of integer commitment. But as far as I know, it's very hard to construct an integer commitment. And I only know how to construct it from on my other group or just the hash.
So material commitment will not work.
And I think if the requirement of adding the size of this is unnecessary, I think of course we can use other groups that such as a bilinear group to conduct the debate.
So let's thank the speaker again. Let's move on to the second presentation. The paper Learner Secure Single Server Aggregation via Homomorphic Masking by Han-Jun Lee, Roger Lin, Antigone Bolikroniadou, and Stefano Tesoro. And Han-Jun will give the presentation.
Thank you for the introduction. I am presenting our secure single server application with key homomorphic mask. The launch work from Rachel, Antigone, and Stefan. motivating application for secure application is federated learning, where a set of endpoints, each holding a local database, wants to jointly dataset wants to jointly train a global machine learning model with the help of server. And to do this, they first train a local models send them to the server to aggregate the models into a global one and send back to each client. The clients will need to train further locally to obtain the updated models, and they need to repeat this process for many iterations. And here, a concern on privacy is that the local models still revealed to the central server may leak sensitive data on the local training side. So instead of sending the local models in clear, what the client can do is to run a secure aggregation mode protocol with the server to help the server learn the aggregation result without leaking anything else about the local model. So abstractly, the secure aggregation problem considers n clients and the server, where the client's input are the high-dimensional integer vectors in Z to L, and bounded by some value B. You can also think of B as the multiples. The server is supposed to learn only the sum and nothing else. And we additionally require that the clients only interact with the server, but not with each other. In this work, we further focus on the setting with many repeated aggregation for a large number of key iterations. In this setting, each client will obtain new input per iteration, and the server is supposed to learn one aggregation result at the end of every iteration. And we'll consider the same set of clients throughout all iterations. This setting naturally allows for a reusable setup run. The setup run could have relatively high cost, but it will be amortized with many iterations. I'll give more detail about our system model. First, the client in our system may drop out at any point, maybe due to crash failure, and they can rejoin at any later iteration. We model this dropout to be statically chosen by an adversary at the beginning of the program. Second, the adversary may corrupt the server together with some polluting clients, and we assume that this corruption happens also adaptively at the beginning, and the corrupted set will stay the same throughout all iterations. Assumption is that less than delta fraction dropout will happen across all iterations, and less than gamma fraction corruption will happen, where delta and gamma are some arbitrarily constant fractions that sums to less than 1. And our protocol will additionally assume a PKI setup, where each client will learn the public key of all the other clients before joining the protocol. So the guarantees are, first, robustness says that if a client drops out to join the first round in any iteration, then its input will not be included in it. But if a client finishes the first one, then its input is guaranteed to be included. And privacy says that the adversary controlling the corrupted server and some clients can learn just the aggregation result, which contains 1 minus delta minus gamma times n. This many number of honest inputs added into a single sum. And this is the return value. So next, I will compare with prior works, but I will focus on the setting of repeated application. And I will consider a large input dimension L that's much larger than the security parameter. For the baseline of the comparison, is the state-of-art protocol in the single session setting by DGD LR20. And to adapt this into the repeated setting, basically we just rerun the protocol for each application, and it takes 4 rounds in the malicious setting. Another subtle point about this protocol is that it's only proven secure against with respect to a leakage function that allows leaking multiple non-overlapping sums, whereas this is slightly weaker than the guarantee I just introduced, which only allows leaking single sum to that. Next is the recent work by GTS DB22. They proposed a system called microfab ML, and this is the first work that takes advantage of the repeated setting, where they have a reusable setup round plus 3 rounds per application, which improves on the baseline. The big limitation of this system is that the server will only recover the results in exponent in a DDH group. So if you want the result in clear, the server needs to compute the discrete logarithm by brute force, and this is only feasible when the inputs are guaranteed to be those. Then it's our work. We also get a reusable setup plus 3 rounds per application. Our technique is different, and we avoid this limitation of having to compute the discrete logarithm. In fact, so we can support modulus that are exponentially. And in fact, our server computation is very fast. It's even faster than the baseline server, as shown in the figure. So I want to mention briefly some other related work that improves over the baseline in other directions. First is the paper, the system called SASH Plus. It's a semi-honest protocol that improves the computation of over the baseline, but they need to add more rounds, even more rounds than baseline. Another work called system called Acorn adds this very important new functionality called input validation to the baseline. And orthogonally, they also introduce new technique using simple morphic PRT to reduce computation over the baseline. But this work, they still consider the single session setting, and it requires 4 rounds per application. Okay, so before going into our actual protocol, I want to start with a strawman solution, which is very inefficient, and it doesn't utilize a setup run as we go through. It's also different from the pairwise masking paradigm that are used by the original journalists at work, secure aggregation protocol and the baseline. But this strawman solution will be conceptually pretty simple and closer to our actual protocol. And I will focus on the semi-honest setting. In the first step, every point in the strawman solution will just secret share a one-time pad or sub I, which is specific for this current iteration T with all other points. And he do this by first computing shares locally and encrypting the shares using the public key of the target point. And this is using the TKI assumption. After having the encrypted shares, we have the server to help forward the shares to the clients. And this first step is really the main bottleneck of the strawman solution, because every client needs to secret share with each other, and secret one-time pad has a large dimension pad. So after the first step, every client can now send its input masked by the one-time pad or sub I, and send this to the server. The server will just compute the sum of the masked input, which already contains the desired output of M sub U, the aggregation result, but it's added with the sum of the masks, which we need to help the server to remove. So to do this, the server will notify each client about this step view that it's considering. And then the client will locally aggregate over the secret shares of the one. So here we can see from with linearity to see that computing the sum of the shares is equivalent to computing the share of the sum of the masks because linear operations. And the share of the sum of masks is exactly what the server needs for the reconstruction. So the server gets those messages and runs a reconstruction algorithm to recover the sum of the masks and subtract it. See again the correctness. We can write out the computation of this sum and see that by linearity we can move around this reconstruction algorithm, switch order of the summation to see that the result is indeed the sum of the reconstructed mask. Okay. So in the Stallman solution, in the next iteration, the client needs to go through the secret sharing step again, which is very expensive. And our goal is to remove this, avoid this step in the actual code. And our main ingredient is this abstract scheme called key homomorphic masking scheme. And I'll introduce something. So in this talk, I'm using a very simplified function. So it looks basically just like a TRF. To compute a mask, you run it with a secret key S and distinct type key. To compute the mask. And the important property is called additive homomorphism, which says that if you add the two masks of the same type, this will translate to adding the underlying keys over the key space. Given this property, we can generalize to see that we can evaluate any linear function over a set of masks, which will translate to evaluating the linear function over the keys. And what we will use is to run reconstruction over the masks and translate this into reconstruction over the keys. So yeah, to see how this masking scheme will help the protocol, we first recall that in the Stallman solution, every client needs to secret share a slash runtime pad and use it to mask its input. And now, instead, every client can secret share its secret keys, masking keys, once and for all during the setup phase. And then during each iteration, they run this masking scheme using its own secret key together with a distinct iteration number that they have. This ensures that every iteration is using a secure mask. And the server proceeds as before. This summation result contains already the aggregation result as desired, and is added with the sum of masks, which we need to remove in the next step. So as before, each client PI will compute the reconstruction message, and it's compute as first it locally aggregate over the key shares, secret key shares into this S sum U I, and run the mask algorithm over the key share. Again, from the homomorphism and linearity of the secret sharing scheme, we can see that running mask over sum of shares is equivalent to taking a share of the sum of masks by just moving the operation order. And the server proceeds as before, runs the reconstruction algorithm to recover the sum of the masks. And to see correctness, we just need to write out to the computation and apply homomorphism and linearity multiple times. So basically, we want to say that with running the reconstruction over the masks, it translates to running the reconstruction on the key shares, and then take the mask, and finally aggregate over the mask. by homomorphism and linearity, we can reorder those operations as we want. And this shows that it actually gets the correct. And this is the protocol, idealized protocol with the treatment of the masking scheme and any linear secret sharing scheme. So to instantiate it, our instantiation uses the learning with rounding assumption. And this construction is really simple. It's heavily inspired by the seed homomorphic PRT mentioned in this paper BLM 13. And the assumption basically says that given a secret, given a public matrix A, random matrix A, its product with a secret vector S rounded down to a sufficiently smaller bodies P is indistinguishable from the random. So therefore, we can use this LWR sample directly as a CDN, computed as hash of T times S, the secret TS, where the hash of T acts as the public random matrix in the assumption. And here H is modeled as the random. And this simple scheme has an approximate homomorphism as shown in the calculation. As shown in the calculation, basically it's saying that adding two rounded values is approximately equal to adding the value first and then take the round. The difference, which we call the rounding error, is at most random. So whenever we homomorphically compute the addition, this will cause an error of most. So with this scheme, the previous protocol looks slightly different because the rounding error arises from homomorphically computing the reconstruction algorithm. And the magnitude of error grows as the coefficient of the reconstruction. And this error also propagates into the final result, so we need to remove it. A simple way is to just scale the input values by a large factor delta. And if delta is large enough, then indeed we can remove the noise to recover the true result. But scaling by a large factor delta is creating significant overhead in the system because the client now needs to use a larger mask to hide the scaled inputs. And this requires a larger LWR modulus, and which will require a larger secret dimension of LWR. This all creates a computation and communication overhead. So to minimize the overhead, our solution is to use a flat secret sharing, which is just a name for the requirement that the secret share and the reconstruction algorithm, they all have just 0, 1 coefficient. But since the coefficients are small, we guarantee that the error doesn't grow by too much, since we minimize the overhead. And to get to construct the flat secret sharing, we note that there already exists such a scheme from the paper BT06, but the limitation is that the total share size is huge, grows with n to the 5.3. And in our setting where the number of client m is really large, this is a prohibitive cost. Just to briefly recall in the setup, each client will need to secret share with every other client. And one idea to minimize the cost is to run this secret sharing scheme within a randomly sampled committee, and we sample the committee during the setup phase once and for all throughout the integration. So here, the setup phase now is illustrated here, where every client just secret share with the community, so the total share size per client becomes lambda to the 5.3 instead of n to the 5.3. And this reduction in the cost comes with the trade-off. First, at the step where we sampled the committee, we're already introducing some negligible failure probability. Because the guarantee we want is that the fraction of corruption and the dropout within the committee should match approximately the true fraction in the population. But with some low probability, this might not hold, and the criterion scheme will have no guarantee. And the second trade-off is that we're selecting a committee in the setup round, and it's fixed throughout the iterations, so that we really need to assume a static corruption level to prevent the adversary from adaptively corrupting the small committee after seeing that they're selected. The paper will further have some optimization to reduce the total share size to even lambda squared instead of lambda 5.3. And this, we get this through further relaxation, where we introduce a constant fraction gap between the reconstruction and privacy threshold. In the end, we essentially, it's still the same scheme as in DT06, but with smaller parameters and some analysis, careful analysis about our relaxation. So given those two ingredients, we can finally instantiate the protocol under the LWR. Our paper also has instantiation under DCR, but I will speak for now. So to recap, our protocol, the first important feature is that it reduces the round complexity by having a reusable setup. Secondly, the server computation is really fast because it only needs to reconstruct a single mask with 0.01 coefficient, which essentially is the addition. Finally, as noted above, in the setup, only the committee member collect secret shares of the keys, and during every iteration, only the committee member will help with the reconstruction. So the non-members, they don't do anything beyond sending a mask input. So non-committee members are selected. And the bottleneck is also the committee client. First, every client needs to store and shares of the keys collected during the setup and throughout all iterations. Second, when they help with the reconstruction, they need to aggregate over at least the number of dropout times. So if the dropout is large, then the computation cost is one solution of follow-up work, subsequent work, Flamingo, which also focuses on the repeated setting. And we also similarly select a random committee to help with reconstruction. So we need a similar static assumption. But they managed to reduce the committee storage requirement significantly, which was one of our bottlenecks. As a trade-off, they have slower computation for both the server and the client. So the open question perhaps is that can we achieve the best of both worlds, and can we try to avoid the static assumptions without hurting?
Any questions from the audience?
Great talk. I remember the capability theory you introduced some noise. The noise has been proved almost.
Yeah.
So can we like we initialize the redefine like we let the shift the operation, one operation will introduce 1 bit noise. So we can left the gratitude, left shift the gratitude 1 bit to avoid the noise we introduce.
I think the noise, it may be 1 or 0. What are we trying to say?
So we put the must that should
Maybe I can ask you for some.
part was so they not the last one bit.
Yeah, maybe a further understand.
Any other questions? I have a related question. So your simplified description of pleomorphic masking looks like a pleomorphic PIF. So can you elaborate more on the major differences between these two primitives?
I see. Yeah. So in the LWR, instantiation is basically the same thing. But we also have the instantiation based on the PCR assumptions. In there, we'll encode the message in the exponent first. So it's not exactly like a PR.
As a general primitive, so is there any difference in the security requirements between masking and PIF?
I think mostly it's just the syntax.
So let's thank the speaker again. Okay, so we go to the last topic session. The paper non-interactive generated functional proofs by Gongsun Zheng, Junju Lai, Chen Kang Huang, Lingzhu Chan, Xiangming Wang, Huqiang Lam, Huasong Wang, and Qiang Wen. And Gongsun will give the presentation. Please.
Good morning. I'm Shen Zheng from Pengcheng Laboratory. Today I will give a presentation on the topic of non-interactive zero-knowledge functional proofs. The presentation committee consists of 4 parts. Firstly, I will talk about the motivations and the backgrounds of this paper. Following that, I will introduce the FINJK primitive. Then a generic construction of FINJK will be introduced. Lastly, I will present a concrete construction for set membership. So first of all, let me introduce the motivations and background of this research. Let's revisit the concept of non-interactive zero-knowledge proof in the common buffer string model. It contains 3 algorithms: set up, proof, and verify. As illustrated in figure 1, the setup algorithm generates a common buffer string, while the proof algorithm produces a proof pi for the statement within pair X omega. Subsequently, the verify algorithm outputs a bit indicating the validity of the proof for the statement X. This system adheres to 3 essential properties: completeness, soundness, and zero knowledge. Soundness issues that the verify rejects a proof for false statement, and the zero knowledge issues that beyond the truth of the statement, the verify cannot know any information else about the witness from an accepting proof. In this paper, our object is to generalize the concept of IJK by enabling the prover to share a witness in a fine-grained manner with verifiers. This means that in addition to verifying the truth of the statement, the verifier can also gain insights into certain functions of the witness using a secret key provided by the prover. To address this requirement, we propose a new type of IJKs called non-interactive zero-knowledge functional proofs, which is short for FIJK. We find several potential applications of FIJK. including supervision, blockchain-based option systems, and anonymous attribute-based credential. Here, we take the supervision for anti-money laundering, for example, to illustrate the promising applications of IZK. In this scenario, the authority generates a public key and a secret key, and all users utilize the public key to generate or verify proofs. Typically, individuals generate zero-knowledge proofs for the regular activities, such as transferring privacy-preserving cryptocurrencies. Then a receiver would accept money when the proof is valid. In certain cases, the authority may authorize a trusted third party for supervision purpose. A secret functional key is generated by the authority and sent to the trusted third party. Consequently, the trusted third party can obtain the specific information from the proofs using the key. This enables them to determine whether a user has violated the rules or not, while ensuring that other information about the witness in the proofs remains undisclosed. We initiate the study of IZK. The specific contributions are outlined as follows. Firstly, we present a formal definition and the security notions of IZK. Then we provide a generic construction of FIZK for any MP language R, which enables the prover to share any function of the witness with the verifier. Finally, for widely used relation about the self-membership proof, which also implies range proof, we can share a complete and efficient FIZK, and we call it self-member functional proof, which is short for SMP. Then let me introduce the primitive of FIZK. A FIZK scheme consists of 7 algorithms set up to verify U-key generation, F-key generation, check key, and extract. Roughly, set up, proof, verify are similar to those of FIZK, except that the proof and the verify also input the prover's public key, which is generated by the user key generation. The prover invokes F-key generation to generate a secret key for some function and distribute it to a verifier. With this key, the verifier can call extract algorithm to extract the function of the witness from an accepting proof. The validity of the secret functional key can be checked via the algorithm check key. If there is no restriction on the extracting capability of the keys, then a verifier with a secret functional key can learn a function of the witnesses from all accepting proofs generated by the prover. To address the above issue, we introduce labels in some of the above algorithms. Concretely, in FIZK, the F-key generation algorithm takes the label tau F, the secret key of the prover, and the function F as input. Then it outputs a secret functional key sk f tau F. Similarly, the proof algorithm takes a label tau P, a public key pk, and a statement witness pair x omega as input. Then it generates a proof pi. In this way, the extract algorithm can output f omega from pi only if the predict function of tau p and tau f equals 1, that is p tau f equals 1. The security property of FIZK contains completeness, functional knowledge, adaptive soundness, and zero knowledge. Completeness of FIZK has 3 requirements. Firstly, any proof pi generated by proof algorithm should verify successfully by verifier algorithm. Secondly, any normally generated secret functional key sk tau f for f and tau f should pass the verification or check key algorithm. Thirdly, for normally generated proof pi and the normally generated secret functional key skf tau f, if p tau f equals 1,
then the extraction algorithm should extract f omega from pi successfully. The functional knowledge property requires that, in general, as long as a proof pi can be verified successfully, the secret functional key passed the verification or check key algorithm, then the verifier can be convinced that a function of some witness can be extracted from the proof when p tau f equals 1. Soundness is similar to that of NIJK. In other words, it is negligible probability that the verifier would accept the proof for a false statement. The definition of the zero knowledge gain presented here is slightly different from that of NIJK. It's formalized in multi-user setting, following that, apart from knowing the truth of the statement and some functionalities of the statement of the witness, the verifier cannot obtain any other information about the witness from the accepting proof. In our zero knowledge gain, we allow the adversary to make secret key generation query to the oracle. For the challenge table output by A2, it's required that A2 should output two witnesses, omega and omega pi here. We suggest that omega pi is not required to be a true witness for the statement X. The law of the witness X pi here is only to provide the corresponding functions of omega to the simulator. Finally, zero knowledge here requires that the proof pi produced by the proof algorithm is indistinguishable from that generated by the simulator. We observe that the zero knowledge proof property of FIJK implies the traditional zero knowledge property. In fact, we conclude that every FIJK scheme trivially provides an FIJK scheme. As shown in theory 1, the transformation is presented in figure 5. Due to time limitation, please refer to our paper for detailed explanation. Next, please allow me to present the generic construction of FIJK. Our goal is to construct a FIJK or general function family. Then let me introduce some building blocks. The first building block is that we define a new function family denoted as f hat. For simplicity, for each pair f tau f, we represent the corresponding functions in f hat as the small f hat here. The second building block is that for the new function family f hat, we have a functional encryption. The third building block is that we have NIJK schemes for the relation RCT and RK. RCT means that omega is a true witness for the statement X, and the C is a well-informed self-test of omega. RK means that the key sk f hat f tau f is a well-informed secret key for the function f hat f tau f. As we know, we can construct NIJKs for any MP language. Therefore, we can construct two NIJK schemes for this relation. After that, we can have the generic construction. The main idea is straightforward. Given a valid pair of statement witness X omega, we encrypt the witness using the functional encryption scheme. In addition to proving the relation about X omega in some relation R, we also need to demonstrate that the self-test is well formed. That is the relation RCT we talked about. Finally, the proof algorithm outputs a proof, including the self-test and the NIJK proof. Extraction can be implemented by calling the encryption or functional encryption. Thus, verifiers can then obtain some functions of the witness by decrypting the self-test using the corresponding secret keys. The secret functional key generated by F-key generation also contains an NIJK proof, which enables the verifier to check the validity of the secret functional key via the check key algorithm. Then we can prove that the generic construction of NIJK satisfies completeness, function knowledge, adaptive solveness, and zero knowledge. For the proof of theory 2, please refer to our paper. Finally, let me show you how to construct a concrete construction for set membership. Set membership proof enables a prover to convince or verify that a digitally committed value belongs to a specified public set. The relation is shown in RSM. A special case of SMP is range proof, where the public set is an integer range. SMP are widely utilized as building blocks in various cryptographic schemes, such as an anonymous credential, Zcash, and eCash. Therefore, you provide a concrete and efficient FIDK for relations about the set membership proof, and we call it set membership functional proof, which is short for FSMP. In FSMP, prover outputs a proof associated with label tau p to demonstrate that the committed value omega is in some set phi, and verify with the secret functional key for phi SF and tau f can additionally check whether omega in phi SF or not from the SFP proof when p tau p tau f equals 1. To construct FSMP, we propose a new primitive called set membership encryption, which is short for SME, and is a variant of public key encryption. It includes 5 algorithms that are key generation, check key, encryption, and query. Roughly, encryption algorithm takes a set phi, a message omega in phi, and the label tau p as input to generate a ciphertext C. The query algorithm takes as input C and the secret functional key for phi s and tau f generated by the key generation, and the query algorithm outputs a bit. It requires that when p tau p tau f equals 1, the query algorithm outputs 1, if and only if omega is phi s. For security properties, we define the correctness and IND security. We say that SME support sigma protocols if they exist a sigma protocol to prove the very formulas of a SME ciphertext. The commitment scheme is another building block. We require that the commitment scheme also supports sigma protocol. One example that satisfies our requirements is the potential commitment, which we can prove by the Okamoto's sigma protocol. Then, for a relation tied RSM, it contains a commitment and a ciphertext of SME. Since for the both parts, they are sigma protocols, we can construct an efficient NZK for the relation tied RSM through the composition of sigma protocols and the Feld-Chalmers transform. Similar to the generic construction of NZK, here we also need to redefine the function family. Each function f in big F indicates a set SF, such that for any statement containing commitment and set phi, and any witness omega x containing omega and RCM, if omega equals 1, if omega in phi SF, it equals 0 if omega in phi but not in phi SF. It returns an empty if omega is not in phi. The main idea of constructing FSMP from SME is also straightforward. Given a valued pair of statement or witness is omega, we encrypt the witness by SME. Verifiers can then obtain F omega by decrypting the ciphertext with the corresponding secret key. In addition to proving the relation about X omega in RSM, we also need to demonstrate that the ciphertext is well formed. That is the relation behind RSM we talked about. Finally, the proof algorithm outputs a proof, including the ciphertext and the NZK proof. Unlike the generic construction of FNZK, the secret functional key generated by key generation doesn't contains NZK proof, since the underlying SME supports an easier method to check it. we can prove that if the underlying SME is IND secure and the supports Sigma protocols, then the FSMP satisfies completeness, function knowledge, adaptive soundness, and zero knowledge. Please refer to the proof for the theory 3 in our paper. To save time, here we briefly introduce how to construct SME from dual IPE, which is another primitive proposed in this paper. The key of dual IPE is a spatial interproduct. It takes as input 4 vectors, x1, x2, y1, and y2. The spatial interproduct equals 0 if both the interproduct of x1 and y1 and the interproduct of x2 and y2 are 0. Otherwise, the spatial interproduct equals 1. The dual IPE is required to be payload hiding and the partial attribute hiding. More exactly, only attribute hiding for vector x1 and y1. Then we can achieve SME by encoding omega and phi into 2 vectors, such that if it holds that omega and phi, the inner product of the 2 vectors equals 0. In our paper, we provide an efficient instantiation of dual IPE utilizing the technicals in IPE based on the K-linear exception. For more details, please refer to our paper. Therefore, and finally, we can construct an efficient FSMP through these building blocks. That's all for my presentation. Thank you.
Time for questions. Okay, so your formulation requires the verifier to obtain a secret key from the prover, right?
Yeah.
How is this instantiated in practice? So, you approach the verifier and you give them the key first.
Not exactly. In fact, the secret key the secret functional key can be generated after the proof is generated. So of course it can be generated ahead of the proof, and of course it can be generated after the proof is generated. It's very fast.
Which means that for the same proof, and if you can generate 2 different keys for 2 different verifiers.
Yeah,
Oh, that's
exactly.
great.
Yeah. Thank you very much.
Any other questions?
The intuitive meaning of power and
Oh, okay. It's a very good question, and let me explain it more. Tau P and tau F here are labels. It used to okay, let me take an example. For example, in the supervision for the anti-money laundering, and the authority may want to just the trust third party to just see if some user maybe they have lots of transform, for example, from for years, but the authority may not allow the trust party to see all the transform. Maybe the authority just allow the trust party to see for a year, for some months. Then it can be used as the label here. For example, the label can be expressed a month from October to September. Then the trusted third party can use the secret key to get information only the transfer within within this year.
it's a proof of that this function doesn't expire, or
It explains something.
does it mean that it's a proof of how f is a proof that this function f still works, doesn't expire?
Oh yeah, exactly. it can be used to
It's still valid, it's a proof that this function is valid.
it can be used like that. Like that.
Thank you so much.
Thank you.
Any other questions? There's no other questions, so let's thank the speaker again.
Thank you.
So we'd like to thank all the speakers of the session again and everyone for attending the session. So now it's time for a coffee break.